Okay, in this video we're going to prove the formula that we probably already know, hopefully, of the area of a circle. There are tons of ways of doing this, but this is kind of a cute problem that I found. We're going to prove the area of a circle using the fundamental theorem of calculus, but you might remember that the fundamental theorem of calculus comes in two parts, and we're going to use the lesser used part to prove this area of our circle. So here are our goals. This is what we want to show. Let me draw a little set of axes here. We have our circle with some sort of a radius, and we'll pretend that it's constant even though my drawing of a circle is not that great. And we want to take a look at this area inside of here, and we'll say our area is pi r squared. Cool. What we're actually going to do though is we're going to take a look at this circle with some radius r, and we're actually only going to look at a quarter of it. And we'll prove that this portion here has an area of pi r squared over 4, and then hopefully we can see by symmetry that if you just multiply this by 4, because there are 4 of these regions, that we'll get pi r squared. So we're actually going to take this second approach. Now, to do this, maybe I'll grab this little picture here. To do this, oh, I've lost my exponent. We're going to need to know a couple of different things. First, we need to know our formula for a circle. Here is our equation that defines a circle. X squared plus y squared equals r squared. This is a circle centered at the origin, which is what we've got here. We want to write this as a function, so we'll be able to say that y squared equals r squared minus x squared. And then we can say y is equal to plus or minus the square root of r squared minus x squared. Now for us, since we're only looking at this first quadrant, all the y values are positive. So we'll be able to use this square root of r squared minus x squared formula without much of a deal. Then what we're going to do is we're going to use some calculus. We're going to set up a definite integral to find this area. We want to find the area bounded by y equals the square root of r squared minus x squared and y equals x from x equals 0. That's our origin right here. We want to go up to this boundary point, which is just going to be the length of the radius. So we'll say 2 x equals r. So we're going to look at this integral. The integral from 0 to r of the square root of r squared minus x squared dx. Now this is a really common integral that people will look at. First, what we're going to do is consider the unit circle with r equal to 1. So that means we're looking at this integral from 0 to 1 of the square root of 1 squared minus x squared. And this is a really common integral that gets done in most of the time in Calc 2. And so in Calc 2, the strategy is to use the fundamental theorem of calculus, part 2, which says the integral from a to b of some function is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. And to find the antiderivative, we would use trigonometric substitution, where specifically what we would use is x equals sine theta and dx equals cosine theta d theta. So this is a classic Calc 2 problem to do. But what I've been doing is been pitching this to my Calc 1 students and trying to get around this idea of like finding an antiderivative for this function here. It's a difficult thing to do in Calc 1, and so our strategy instead is going to be using the fundamental theorem of calculus, part 1, which a lot of people may not actually remember. So that's going to be a little bit interesting. We'll build up to this, and I'll remind you what the fundamental theorem of calculus part 1 is, and let's go ahead and start this thing. So what we're going to first do is create a function. So we want to turn the integral from 0 to 1 of the square root of 1 minus t squared dt into a function output. And the way that we're going to do that is we're going to define some function. I'm going to call it capital F of x. And what I'm going to do is I'm going to change my limits of integration to be not constant values, 0 and 1, but function values. I'll call it a of x and b of x. And you'll also notice that I switched my variables here from x to t. And that's just because I'm going to make my function be a function of x, and I want my limits of integration to be the things that are changing. I don't want my variable in the limit of integration and in the integrand at the same time. That's going to be tricky. So then what we're going to have is our integral be some sort of a value, a of c up to b of c, where hopefully a of c is equal to 0 and b of c is equal to 1. So what we need to do is find 3 different things. We need to find 2 functions, one for a and one for b, and we need to find an input, c, where when you plug that into whatever functions we've picked, a and b, they give us 0 and 1 at the same time. So what we're going to do is we're going to let a of x be the cosine function, and b of x be the sine function. So now what we have is that capital F of x is equal to the integral from cosine x up to sine x of the square root of 1 minus t squared dt. And we need to find a value that we can plug in for cosine and sine to make it 0 and 1. And that should be not too bad, because if we think about our unit circle, there's a point right up here on our unit circle. We have our axes looking like this, and this point is 0, 1, where cosine is 0, sine is 1. This is at an angle of pi over 2. So what we want to do then is find capital F of pi over 2. So notice, instead of actually integrating this thing using the second part of the fundamental theorem of calculus, we're just going to create this weird bulky function, and if we can find a nice way of writing this function, we'll evaluate that function at pi over 2, and we'll be done. So the question is, if capital F of x is equal to this integral of cosine x up to sine x of the square root of 1 minus t squared dt, what does the fundamental theorem of calculus say about this? And here's the fundamental theorem of calculus part 1, the part that we're going to look at specifically. So notice this is not the part that says find the antiderivative or one of the antiderivatives of your integrand and evaluate it at your limits of integration. No, this says if capital F of x is an area function, sometimes we'll call it an integral from some constant a up to variable x of some function g of t dt, and g is continuous on some interval a to b with x in that interval, so x is a variable that's going to take on values in between a and b, then capital F of x is continuous, and thus it means it's differentiable, and differentiable on that interval, with the derivative being exactly this. Capital F of x, or capital F prime of x, sorry, is the derivative d over dx of that integral, which is just the height of our integrand at the variable ending point. This is kind of a weird theorem. And when this gets pitched to students in Calc 1, in my experience teaching Calc 1, this is like a really quick thing for them to forget and to pretend, well, it doesn't really matter. In most Calc 1 classes, when I've seen this used, and I'm guilty of this myself when I teach Calc 1, this is used to prove the second part of the fundamental theorem of calculus, which is the one that matters, kind of. And I'll say that sarcastically because I think this actually does matter, but it's hard to see why. Anyways, let me sketch out a quick explanation. This isn't going to be a full proof of this idea, but at the very least it'll be an explanation of what's going on, and hopefully we can see that, yeah, this theorem does make a bit of sense. So I'm just going to draw some function here. We'll call this my g of t function. And let's say I've got a right here, and I'll put x up here. Then we can see pretty easily that by the way that we defined capital F of x, it was this integral from a to x of g of t dt. So it's this area. So that's why we call this an area function, because it's a function that literally spits out the area under this g curve from a up to this moving ending point. And if we changed where x was, then our area changes, right? We add a little bit more. What we want to do is we want to look at the derivative of this. So we're going to think of what is capital F prime of x, and I'm going to use the limit definition of the derivative. The limit as h goes to 0 of capital F of x plus h minus capital F of x all over h. And if we just plug in these into our definition of this function, this is a limit as h goes to 0 of the integral from a up to x plus h of g of t dt minus the integral from a up to x of g of t dt all over h. So I'm going to draw this. I'll draw another little line. I really should get straight lines for this. Let me get a nice straight line for this yellow line. I'll use my ruler. There we go. That's better. All right, and now what I'm going to do is I'm going to draw another line right here. That's very, very close. And this is going to be at x plus h. And so h is just this tiny little difference in here. Notice then that the integral from a to x plus h minus the integral from a to x is just this sliver. So this should make sense. When we're thinking about the derivative, we're thinking, what's the rate of change of this area? How does our area change when we bump this ending point a little bit, when we just nudge it? I want to zoom in on this right here, really the whole picture of our graph, but let's draw this again. So let me draw my axis. Here it is. And I'm going to try and zoom in where it counts. And oops, I forgot to take my ruler off. Here. And here's x plus h. And I'm going to say, here's my function. Now, this isn't accurate because I'm scaling it all weird, but oh well. And we want this area right under here up to here. What we're going to do is just approximate that area using a rectangle. Maybe I'll pick any rectangle. I'll pick like if you remember Riemann sums, I'll pick like almost a midpoint rectangle. Doesn't really matter. I'm going to approximate this area this way. Notice that this area is hopefully the same thing as the actual area. The mean value theorem of integrals says that we can always find a rectangle that will do this. So let's just pretend that I picked it perfectly where these areas do match up. And then what we'll really notice is that this little change in area that we have, maybe I'll rewrite this. My integral from x to x plus h, that's this area that we're looking at, over h. What this is really equal to is an area, and h is a width. So what I've got here is this tiny little area divided by a width, and that's going to give me height. The height of this is going to be some function height at whatever that point is, right? We'll call it x naught. So our height in this case is g of x naught. But now let's think of what happens when this limit as h goes to 0 gets put in there. When h goes to 0, these two ending points get smushed together, and so this middle height is essentially exactly equal to g of x. Or g of x plus h, but when h goes to 0, again, they're the same thing. So the derivative of this area really is the height at the end here. Okay, so that's just a really quick, really brief, really basic, not full proof, but hopefully a little explanation of this fundamental theorem of calculus part 1 that people skip over a decent amount. All this to say is, so if the derivative of this area function is g of x, we want to know what is capital F prime of x the way that we've defined this. Well, that's going to be a derivative of this integral that we set up of cosine x up to sine x of the square root of 1 minus t squared dt. And you'll notice that this is a little bit different because while this here is just going to be our g function, we don't have a constant. And this is not just x, it's a function of x. So that's kind of tricky. So what we're going to do is use some more properties of integrals to split this thing up a little bit. So we'll say capital F prime of x is really equal to the derivative of, I'm going to split this up to say it's my integral from cosine of x up to 0 of the square root of 1 minus t squared dt, plus the integral from 0 up to sine of x. So I've just cut this thing in half at 0 and split it into two separate integrals that I can add together. What I want to do is flip the order of these things. So I'm going to reverse the limits of integration on this, and in doing so, I'm going to have to add a negative out there. I'll reverse the sign as well. Okay, so now we have two integrals, both set up with constants in our lower limit of integration, and then functions of x in our upper limits of integration. So it's still not x in that upper limit of integration. It's a function of x, but that's no big deal. We'll figure that out in a second. I'm going to apply my derivative across this sum, and so this is going to be the negative derivative of the integral from 0 to cosine x of the square root of 1 minus t squared dt, plus the derivative of the integral from 0 to sine x of the square root of 1 minus t squared dt. And for both of these, we're going to have to use the chain rule because these are functions of x. All right, so let's go ahead and do that. Capital F prime of x is going to be the derivative of this first integral, which the derivative rule says it's going to be the height of that g function, that square root function, at the endpoint, cosine of x. But now, since we're using the chain rule, we're going to have to multiply by the derivative of cosine of x as well. So what this is negative square root of 1 minus cosine x squared. That's our 1 minus t squared evaluated at cosine x, times the derivative of cosine of x, which is negative sine of x. Then we'll add the derivative of the second integral, which is 1 minus, instead of t squared, we evaluate that at sine of x, and we multiply by the derivative of sine of x, which is cosine of x. All right, so a negative sine times negative is positive sine of x times the square root of 1 minus cosine squared x plus cosine x times the square root of 1 minus sine squared x. And you might notice that there's some Pythagorean identities in here, right? Sine squared x plus cosine squared x equals 1. So that means that sine squared x equals 1 minus cosine squared x, and cosine squared x is 1 minus sine squared x. And we've got those things, right? So this is sine of x times the square root of sine squared of x, which is sine of x, plus cosine x times the square root of cosine squared, which is cosine x. Well, this is sine squared of x plus cosine squared of x, which is just 1. All right, okay, so let's just figure out what the heck happened. We differentiated this weird function that we set up, and by the magic of the way that we set it up, we got that the derivative was 1. If f prime of x is equal to 1, what's f of x? Maybe I'll leave it here so we can think about it for a second. Hopefully we know that if the derivative is constant, that means that the function is linear. And specifically, we know what the slope is, right? It's a linear function with slope 1. So we know capital F of x is just x plus some constant of integration, c. Okay. Well, now what we can do is use some initial value stuff to see what's going on. So what we need to do is come up with an actual value for our function, something that we know, and we'll remind ourselves our function, that way that we had it written, was the integral from cosine x to sine x of the square root of 1 minus t squared dt. And it seems like, oh boy, it's going to be really hard for us to get a known function value out of here until you notice that sine of pi over 4 and cosine of pi over 4 are the same thing. This is the integral from root 2 to root 2 over 2. Sorry, root 2 over 2 to root 2 over 2 of 1 minus t squared under a square root. I don't have to know much about this to know that that area is 0. So what I've got is that f of pi over 4 is equal to 0. And if I know that my capital F of x function is in this form, and it has this initial value, what I can do is say 0 equals pi over 4 plus c, and solve for c. C is obviously negative pi over 4. What that means is that capital F of x is really just x minus pi over 4. So this integral that we set up is really just this linear function x minus pi over 4. Okay, remember what our goal was. We wanted to find capital F of pi over 2, which would give us this integral from 0 to 1 so that we could show the area of our circle, right? So let's do it. If capital F of x is x minus pi over 4, then capital F of pi over 2 is just pi over 2 minus pi over 4. So what this says is for the unit circle with radius 1, this area right here is pi over 4. And I'll draw in this radius so we make sure we know r is equal to 1 on this. So that's not too bad. Then what we can do is multiply this by 4 and say, all right, so if we were looking at a big area for this circle, again, unit circle, you can forgive my drawings. Oops, I need to get rid of this. There we go. That area is pi, which does check out with what it would be with pi r squared, right? If r is 1, then our area is pi. Cool, great. So now what we might want to do is say, well, does this work in general, though? We did this for a specific radius. What about the more general radius where we just leave everything as r? Not too big of a deal. So what we're going to do now is set up our function again. Capital F of x equals an integral, I'm going to say from r cosine x up to r sine x of the square root of r squared minus t squared dt. So the stuff that I've changed is in yellow. Instead of a radius of 1, I've just put in r, and r in general. Okay, so now when we differentiate it, maybe I'll still set things up and say like, okay, we're still going to have this negative integral from 0 up to r cosine x of square root of r squared minus t squared. We're still going to do all this kind of cut the integral up, flip around the limits of integration when we need to. And now, when we look at the derivative, we're going to say this is negative the square root of r squared minus r cosine x squared times the derivative of r cosine x, which is negative r sine x, plus the square root of r squared minus r sine of x squared times the derivative of r sine of x, which is r cosine x. And what you'll notice is that we get r squared times sine squared x plus cosine squared x, which is just r squared. Now this is still a constant, so that still means that our antiderivative of this, the function capital F, is linear. But now it has a slope of whatever r squared is. We can still use this same initial value. So we can still say, all right, 0 is equal to r squared times pi over 4 plus c. So now c equals negative r squared pi over 4. And so that means your function is really r squared times x minus pi over 4. And so again, evaluating this at pi over 2, is just r squared pi over 2 minus pi over 4, which is pi r squared over 4, which, if you remember, that's exactly what we wanted to show, right? This is the area of a quarter circle, so the area of a circle is pi r squared. All right, summary. Why do we even do this? First, I think it's really helpful to just remember that the fundamental theorem of calculus comes in two parts, and it's really easy for us to just focus on the second part. Students always focus on this idea of a definite integral can be evaluated in this way, which is great. It's a really helpful tool. But the first part of the fundamental theorem of calculus is really, really important. It tells us that antiderivatives exist, right? We have this really nice way of guaranteeing that. The second thing is you don't always need a complicated integration method to evaluate these definite integrals. Now, you might argue that the integration method, integration by doing a trig substitution, is actually easier than the stuff that we just did, because it's kind of bizarre to work through what we've just done. But we don't always need a complicated integration method to evaluate definite integrals. We can map them to function values, which is a kind of cool thing. And then the third thing is that, hey, if you want to do this, you got to be clever with setting up an area function so that differentiating it is actually helpful. You could go back and, when we make selections for the functions that we're going to use for our limits of integration, you could pick other functions that give those same kind of limits of integration. But the problem is when you set things up with your differentiation, we won't get those nice trig identities, and so they're going to end up being like really nasty to work with. So in this case, we were pretty clever about using those trig functions to get those identities to work out. I thought this was a pretty cool problem. This is actually something that I found in a small article by a professor out of the University of North Florida, whose name is Denis. Maybe I'll link to a spot where you can look at the abstract of the article, and if you have access, you can download it. But I thought it was a pretty cool problem, and I've been showing it to my calculus classes every now and then. It's a fun thing. Hopefully this sparks some appreciation for the first part of the fundamental theorem of calculus, which is often a little bit overlooked.